Okay, so let's be real. Like, who here hasn't looked at like a weather report and been like, what on earth does any of this mean?
Yeah.
Or tried to, I don't know, wrap their head around climate science and just felt completely lost.
It can feel like they're speaking a different language sometimes, for
Yeah.
sure.
But what if there was this way to take all that really complex data, like rainfall or those crazy temperature swings, and make it like way easier to actually like understand, faster to learn from,
Yeah.
and get this potentially even more accurate.
Now that would be a game changer.
Oh, absolutely a game changer,
Yeah.
right?
Yeah.
And guess what? That's exactly what we're diving into today, right now. We're digging into a brand new paper, like hot off the presses, October 2024. And it's tackling like this exact problem head on. It's called Learning Non-Gaussian Spatial Distributions via Bayesian Transport Maps with Parametric Shrinkage.
All right, so that might sound a little intimidating, I'll admit,
Yeah.
but trust me on this one, it's way more interesting than it might sound at first.
Okay, so let's break this whole thing down. So imagine, right, you're trying to get your head around something massive and messy, like how rainfall changes across, I don't know, like a whole country.
Yeah, yeah.
Right. That's what we're talking about when we say spatial distribution. But here's the catch. In the real world, we often only have like a tiny, tiny amount of info to actually work with.
Especially when it comes to something like climate science, right? Where getting new data can take like years because these climate models are so massive, they just take forever to run.
Oh, tell me about it. It's like trying to, I don't know, solve a 10,000-piece puzzle, but you only have like a handful of pieces to start with.
Right, right.
And to make matters worse, like these traditional methods, they often just assume that everything fits neatly into like a perfect little bell curve.
Yeah, like it's all nice and predictable.
Right. Which, that's rarely how it actually works in the real world.
Especially not with something like the weather.
Especially with the weather. So unpredictable. So we're stuck between this rock and a hard place.
All right, too. Yeah.
Because we need to make sense of this incredibly complex data, but we just don't have a lot to go on. And then on top of that, those traditional tools just aren't cutting it. And that's where this paper swoops in with like this really cool idea, transport maps.
Okay, so imagine, right, you have this giant, like, crumpled up map, completely impossible to read. A transport map is like finding, like, this magical way to smooth it all out.
Okay.
So you're transforming that messy data into something way more organized.
Okay. That's a pretty good visual.
Right.
So instead of just wrestling with those messy rainfall patterns directly, we use this transport map to make them like easier to actually wrap our heads around.
Precisely.
But here's where things get like really, really interesting. This paper, they introduced something they call ShrinkTM, short for shrinkage transport maps.
Yeah, that's you.
I know. And what's really, really cool about this ShrinkTM thing is that it seems like it's designed to work wonders even when you have hardly any data to even begin with.
Yeah, like very, very little.
Like almost nothing.
Well, I mean, in some of the cases they looked at, they were able to get like crazy accurate results with just a single data point.
Wait, hold on. Are you serious? So you're telling me the ShrinkTM can take something as simple as like one day's weather and use that to understand like patterns for like a whole month?
That's the general idea, yeah. It uses this really clever concept called, well, they call it shrinking towards a base model.
Shrinking. Okay, so is it like shrinking the problem down?
It's a bit more nuanced than that. Imagine like you're sculpting with clay.
Okay.
Right? Sometimes it's just easier to start with like a really basic shape, like a rough draft almost, and then you kind of mold and refine it as you go rather than trying to create something, super intricate from scratch.
Right. Okay, that makes a lot of sense. So ShrinkTM, it doesn't start at zero.
Exactly. It starts with like the simplified model, kind of like a generic starting point.
Okay.
And then it uses the very limited data you do have to, refine it, adjust it, really make it fit the specific situation you're looking at.
Oh, okay. So it was like giving the data a little nudge in the right direction, kind of like using this basic starting point as like, I don't know, jumping off point.
Yeah, precisely. And to make that whole process even more efficient, I guess, ShrinkTM uses something called the Vecchia approximation.
Okay, now we're getting a little technical here. What is that exactly?
Okay, so think of it like this, right? Imagine you're trying to get through like a huge maze. But instead of trying out every single path, this approximation basically lets you quickly rule out all those dead ends
Okay.
and just focus on the paths that seem the most promising,
So it's like, what, a shortcut? Like a shortcut for the analysis, the data.
Exactly. It's like a super smart shortcut that makes that whole process so much faster,
Yeah.
which is really important when we're talking about huge data sets, like especially for things like weather forecasting, where, time is really of the essence.
Yeah, because no one wants to wait like a week for the weather forecast. We need to know, like now.
Exactly. And the best part is, this paper, it doesn't just stop at the theory. They actually put ShrinkTM to the test using, like, some real-world simulations.
Oh, that's always my favorite part. So how did it, like, spill the tea, give it to me straight?
In a word, impressive.
Right.
They ran ShrinkTM through a couple of different simulations, and it, like, consistently outperformed those more traditional methods, even when those methods had way more data to work with.
Wait, hold on. Are you serious? So you're saying ShrinkTM, even with its, like, limited data starting point, it still beat out the competition? Like the competition that had, like, tons of info to work with.
It's true. I think what really blew me away was just how accurate ShrinkTM was, even with, like, the absolute bare minimum of data. I mean, in some instances, they literally used just one sample to make these predictions about a much, much larger system.
A single sample. So, like, you mean using, like, 1 day's worth of, I don't know, temperature readings to try to predict, like, an entire month of weather pattern.
You got it. And what's really cool is they actually, like, visualize this whole thing. You should check out Figure 2 and Figure 3 in the paper. It really brings it to life.
Okay, so we're not just talking about, like, numbers on a spreadsheet. Like, we can actually see the difference that ShrinkTM is making.
Exactly. Those figures, they really show how ShrinkTM can capture those subtle patterns, those little complexities that those other methods just completely miss. It's like one of those spot the difference games. Suddenly you see all this stuff you never even noticed before.
Okay, so we've got this, like, super-powered tool that can handle this crazy complex data, even with practically zero information.
Yeah.
And it even gives us, like, visuals to help us understand it.
It's pretty amazing, right?
It is. But okay, let's get real here. How does this actually apply to something like, the real deal, like weather forecasting?
All right, so that's where things get, I think, really exciting. They took ShrinkTM for a spin using some data from something called the Community Earth System Model, or CESM for short.
CESM. Okay, that sounds familiar. That's like the big kahuna of climate models, right?
Oh, yeah. It's a really big deal. CESM, it's this incredibly complex, sophisticated computer model that scientists use to understand how our climate works, how it might change in the future.
But I bet it takes, like, a ton of computing power to actually run that thing. Like, probably uses more electricity than my entire neighborhood combined.
Yeah, you're not wrong, huh? It is a massive undertaking to even run a single simulation on CESM, which is why a tool like ShrinkTM could be such a game changer.
Because it can, like, squeeze every last drop of insight out of that super valuable CESM data, even if we can only afford to run a very limited number of simulations.
Exactly. And in the paper, they specifically focused on using ShrinkTM to model precipitation data from CESM, like looking at rainfall patterns across, like, this huge chunk of the Western Hemisphere.
So they're taking this highly detailed climate model, and they're using ShrinkTM to understand something as specific as rainfall.
Exactly. And even with this limited data, ShrinkTM was able to capture those really complex, long-range dependencies in rainfall patterns, like those connections between the rainfall in one area and then what happens miles and miles away.
So it's not just telling us, like, how much rain fell on a certain spot.
Yeah.
It's revealing, like, these hidden relationships, like these ripple effects across the whole system.
And that's what's so groundbreaking here. Those long-range dependencies are so difficult to model accurately, especially with limited data. But Figure 6 in the paper, it really shows how well ShrinkTM can actually capture those long-range correlations. It's pretty mind-blowing.
Whoa. It's like ShrinkTM can see the butterfly effect, but, like, for weather. How a change in one spot can lead to something huge miles away.
It is a pretty fantastic analogy, and it actually gets even wilder. They didn't just use ShrinkTM to understand, like, past rainfall. They actually took it a step further with something called, get this, conditional simulation.
Oh, right.
So picture this, you've got like this mostly blank weather map.
Okay.
Right. You only know like the rainfall for maybe a few scattered locations.
So it's like having those first few pieces of a jigsaw puzzle,
Exactly.
but you're still missing like most of the picture.
You're exactly right. But using this conditional simulation thing, they showed how ShrinkTM could actually predict what the rest of the rainfall map should look like.
Wow.
Even with all those gaps in the data. Figure 8 in the paper, it really drives this point home. You can see how ShrinkTM basically fills in all the missing puzzle pieces, all those areas where there wasn't any data to begin with.
Oh, wow.
And it does it in a way that aligns perfectly with those long-range dependencies we've been talking about.
Okay, so it's not just like, I don't know, throwing darts at a board and hoping for the best. It's actually like ShrinkTM is, I don't know, connecting the dots. It's seeing the hidden relationships in the data to paint that full picture.
Precisely. And to really, really put ShrinkTM to the test, they actually compared it against those more traditional methods, and they used like a scoring system, kind of like grading their homework.
I like it.
Right. This scoring system, it's called a logarithmic score, and it basically just measures how well each model's predictions actually matched up with what really happened.
Okay, so it's like a report card for accuracy.
Yeah, you could say that.
So, all right, give it to me straight. How did ShrinkTM do?
Let's just say it aced the test.
Yeah.
ShrinkTM consistently outperformed those other methods, which I think really proves that this whole shrinking approach, it isn't just some clever trick, it really delivers.
This is incredible. So we've gone from like completely overwhelmed by all this complex weather data to having this amazing new tool that can make sense of it all, even with hardly any information to start with. But why should all of this matter to, someone like me or our listeners who, maybe aren't like meteorologists or, climate scientists?
Yeah, that's the million-dollar question, right? This isn't just about like fancy math or complicated models. It's really about using the information we have to make smarter decisions. Think about it. In a world that's facing, climate change, faster and more accurate climate predictions, those are essential.
Yeah.
ShrinkTM, this could be like a total game changer. It could really help us understand how our climate is changing and what we can actually do to protect our planet.
Yeah, it's like having a much clearer crystal ball to look into the future, even with all that uncertainty that comes with something as crazy complex as climate.
And the really amazing thing is that these applications, they go way beyond, just weather and climate. The paper even hints at, like, all this incredible potential for ShrinkTM. They suggest that it could be used to understand, like, all sorts of complex systems. Like, what if we could use it to predict traffic jams before they even happen?
Oh, wow.
Or maybe even get ahead of disease outbreaks and save lives. Or even, if you're into it, make sense of the stock market.
Okay.
The possibilities are really endless.
So basically we're talking about anything where you need to make sense of like mountains of data.
Yes.
But you only have like a few little pieces of the puzzle to work with.
Exactly. It really makes you wonder if we can unlock all these secrets about something as unpredictable as the weather, what other mysteries are out there, what other aha moments were just waiting to be discovered.
Now that is something to think about. And on that note, we are wrapping up our deep dive into this incredible world of ShrinkTM. We hope you enjoy this little journey into the future of data analysis, where even a teeny tiny bit of information can go a long, long way. Thanks for joining us, and we'll catch you in our next deep dive.